Okay. We actually might not have much of a class today just because I don't have a lot of pages of notes. This is it. But at least that means I can take my time. Oh. Wait a minute. These are notes from my other class. Hold on. You definitely do not want me to cover that for the graduate class. But yeah, this is all I got. So at least I can be thorough. So here's what's going to happen over the next couple of weeks or so. Today's topic, which will be differentiation and integration of power series, that is the last topic that is considered fair game for the midterm. The midterm is I'm leaving space deliberately here. For March 8th, 2 weeks from today, the class will be taken up by the midterm. The class before that, from Monday the 6th, that will be a review. For the midterm, the practice test and its solution are already posted in Canvas on the main page. Okay. All right, so you should be able to access it there. There was 2 documents. One is just the test questions. So if you want, you can try working them out without knowing what the answer is supposed to be, and then look at the other document, which has a full explanation of how they're solved. Now, one thing I want to call your attention to in the practice test. On the last page, I made a decision over weekend when I was over break when I was writing the test, a list of convergence tests. I mentioned that I was going to post this anyway, but I made a decision over a break when I was writing a test. Just go ahead and include it in the test, because even if I list in front of you, you still got to know how the tests work. So it's not like I'm giving away the store there. Okay, so you don't try to memorize each and every one, but you have to also, what's not going to tell you is like, when do you use a particular test? There are certain cases where different tests are called for. So be sure to make use of that. So what you see in the practice, this will be included in it. So then you know it, you'll have that exact same document on the last page of a real test. So you could just tear it off and have it handy. Okay. So this will cover everything from the beginning of the class until today, about sequences, series, power series. Okay. I need to talk about next week. So Monday, the 27th, and Wednesday, 1st. I'm not going to be around. I'm going to be on the other side of the world at a conference. What I've done, what I did yesterday, Monday, is I've pre-recorded lectures on the notes for those days. It's all about Taylor and McLaren series. So even though I'm covering that next week, that will not make an appearance on the midterm. It may make an appearance in the final though, because the final will be on everything since the midterm. So if you go to the main page in Canvas, where I have links for all of the class meetings from the beginning. So if you follow that kind of link for these 2 days, you'll find the links to the videos there. Yeah.
So how many questions will be on the midterm?
I was going to mention that and it slipped my mind, but I'm just going to open it up and check. Dang it. Okay, there are 12 questions. Okay, so first, there are 4 questions that are on sequences. 5 questions on, I guess you can call them regular series. Actually, 6 questions on regular series. The last 2 questions are on power series. Okay. Hold on, someone was having trouble getting in. Okay. Okay, I'm not sure what's going on there. Okay. We'll see how that goes. All right. All right, so that's a bit of a breakdown of the types of questions. And keep in mind, if it wasn't a practice test, they give you an idea of a sorts of types of things that can be asked. There will be substantive differences between questions on practice tests and those in the real test. In terms of what are the particulars. So don't just do a practice test problem on a real test. And yes, some students are do that very ill-advised thing. You're just tossing away points. The purpose of practice tests is to make sure that there are no surprises on a real test. Because last thing I want to hear is someone saying, "Oh, I wasn't expecting that." You know what to study. There's no excuses like that. Okay. All right. Now, these videos are not posted yet, but they wanted to have today's class done first, but I will make them available soon, along with the notes that go through us. Now, I should mention, all I'm doing in those videos, using just going through the notes that I'll be posting anyway. So because it's I'm just doing this in my office. You all are not around to ask questions. I end up going through them a bit faster than I would if I was here in front of you. But I figure you're watching a video, so you can pause, go back and watch again if you had trouble following the first time. Also, the videos are not terribly long, but they are definitely not a full class period. Okay, actually, I can check. We have a one from a Monday class. Okay, that's 44 minutes long, and the other is only 31 minutes. So, okay. 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 Um, okay, and then the homework for next week's material, that's not due for a while. Check the due dates on upcoming assignments. Okay. All right, so homework 4 is due today. On Monday, the quiz for the first module on sequences and non-power series is due. And then the following Monday, March 6th, which is a day of review, is when homework 5 is due. Now, one thing I want to point out though about homework, so in terms of homework assignments, the coverage deals with homeworks 1 through 6. And all this stuff is homework 7. That's definitely not due for a while. Now, homework 6 is actually due after the midterm. It's due March 20th. The reason why I did that was because I wanted to space, I didn't want to have too many assignments due dates too close together. So for the purpose of preparation for midterm, I still recommend that you try working through it beforehand. But that way, if you end up falling behind, you don't have to expend a late pass. So in other words, you handle how your test preparation however you want to. I'm doing this in the interest of flexibility. But I wanted to point that out that just because the assignment happens to do after the midterm doesn't mean that the material isn't on the midterm. Because there's going to be later deadlines for the end of the semester that are going to be close together, unavoidably so, unfortunately. But I didn't want, certainly I'm not about to have any assignments due over spring break. Okay. Yeah, so after homework 5 is due, there's not another homework deadline for another 2 weeks. Okay, then the homework 7 is due a week after that, March 27th. Okay. So any questions about midterm, stuff like that? Okay. Okay. We have differentiation and integration of power series. Um, Now, see in some cases how you can obtain the power series for a given function or given a function, find a power series. And what we'd always do is relate them to relate the function in question to a geometric series, because we know what the series is for like 1/1 minus x. Now, you can expand our repertoire of the kind of functions we can find power series for if we take into account taking the power series and taking its derivative term by term, or its antiderivative term by term. Okay. And it turns out that getting the radius of convergence for a power series when you take a derivative or integral of one is straightforward, because if you have a power series and you know the radius of convergence, and then you take the term by term derivatives of a power series or its integral, the radius of convergence is the same. Actually, I wasn't planning to do this, but I know I have time. I can explain why. Suppose I'm given a generic power series. Function f of x. Some cn x to the n. All right, so it happens to have a center of 0. So I can differentiate both sides of this equation. So in case of a power series, I'm doing what is referred to as differentiating term by term. So on the left side, I'm just going to have f prime. On the right side, so Cn is just a constant, so that's just going to stay the same. And then I take a derivative of x to the n. Well, it's the simplest kind of derivative we got. So we have n x to the n minus 1. Now, I haven't written my limits here, but so I want to point out, if this starts at n equals 0, so I'm going from 0 to infinity, where's this going to start? I mean, I could start it at 0, but if you keep in mind terms that might be 0, therefore don't need to include them. I mean, I'm obviously going to go off to infinity, but where should it start?
1.
Yeah, at 1, because the first term of this series is just C0, C0 plus C1x, so on. I take a derivative of each of these terms, the derivative of the first term is going to be 0. So there's no point in starting at n equals 0. I can start at n equal 1. Okay. Now, suppose I wanted to apply the ratio test to both of these series in an attempt to figure out the radius of convergence. Ratio test to get what I've been referring to as big old capital R, the radius of convergence. Now, for the first one, I'll be taking the limit. All right, so it's for f of x. Taking a limit as n goes to infinity of Cn plus 1 x to the n plus 1 over Cn x to the n. Now, I don't know what Cn is. I'm just making up a generic power series, so I'm not going to be able to figure this out all the way, but that's not the point. What I'm going to get is, so this xn plus 1 over xn, that's going to simplify to x. So what I end up with is Cn plus 1 over Cn times the absolute value of x. So whatever formula you have for these, you figure out what the limit would be, and that will lead you to your radius of convergence. So in fact, what I can say is the radius of convergence. Okay, because I want this to be less than 1 for convergence. So R is going to be equal to the limits. Yeah. As n goes to infinity of 1 over this, whatever it is. So Cn over Cn plus 1. Okay. Assuming that limit exists, which it may not. But for now, we'll assume that it does. Okay. So that's F. Now we'll do the same for F prime. All right, so I take the n plus 1 term, so that's going to be Cn plus 1, n plus 1, x to the n. So I replace n by n plus 1 throughout this expression. Over n times n times x to the n, n minus 1. Okay, so now I simplify what I can. And I have Cn plus 1 over Cn again, that part doesn't change. And then I have n plus 1 over n. And then I also have the absolute value of x. And I still want this to be less than 1. So it's not exactly the same expression. But what's happening to that part? Just that part, as n goes to infinity.
Just n?
What's the limit of this fraction?
And it's 1.
1. Yeah, because I can also write this as 1 plus 1 over n. So this goes to 1. So, so the radius turns out to be the limit of 1 over this. Assuming that limit exists. It's exactly the same. So the ratio test applied to F versus F prime, those two series, the only difference was this extra factor here for derivative, and that converges to 1. So, so that's why the radius of convergence doesn't change. And if I were to go the other way, where I start with this series, and then I take this antiderivative term by term and apply the ratio test above, I'd have a similar situation where I have the same limit as up here, but times some other factor that's also going to 1. So, so when you take a term by term derivative integral, doesn't change the radius of convergence. Any questions about what happened here? Okay. Let me show you a few examples of term by term differentiation or integration. So a function I have is 4 over quantity 2 minus x squared. Now, this is not previous examples involving going back and forth between function and power series. You try to relate the function to some of the geometric series, but you can't really do that in this case because you have this squared. But if you keep in mind that f of x is equal to g prime of x, where g of x is this function, 2x over 2 minus x. Now, that seems a bit odd. Now, I know it's exactly what I have written here in my notes, but these notes were written back in 2009. And I cannot trust that there isn't some mistake made that long ago. Let's confirm this. If I were to take the derivative of this, I would need to use the quotient rule. That is going to lead to a 2 minus x quantity squared down below. Okay. So we have x times derivative of this, which is 2 minus 2x times derivative of this, which is minus 1 all over 2 minus x squared. And what happens is here I have, okay, 4 minus 2x plus 2x. So, wow, I was right. Go figure. All right. Okay. What's throwing me off here is I believe it's possible to have a simpler function than this. Be the derivative of, have a derivative of f. Because if I rewrite this as 4 times 2 minus x to the minus 2, I can certainly integrate those. So the integral of f okay. Well, what would the integral of that be? That's not your Cal 2 knowledge.
For 2 minus x.
Yeah, so I'll arrive at that. Okay, so before just sitting there, and then I have 2 minus x. Whoops. Oh, you know what? You said, what did you say again?
Okay, I don't know if I got the negative on the board, but it is.
Okay, yeah, okay, so but the power we do 2 minus x to the minus 1 over minus 1. But because it's a minus x in here, that gives you additional factor of minus 1. So you just get 4 over 2 minus x. Okay. Now, I now have two functions, this one and this one, whose derivative, both their derivatives are this function right here. And that is in no way a contradiction, because why? How does it make sense that I have two different functions whose derivative is the same? When you were in Cal 2, and you'd be tasked with working out integrals, I'm talking about indefinite integrals like this one. What did your Cal 2 teacher always nag at you to do?
Oh, let's see, the coefficients.
Yes, antiderivative is not unique. They all differ by a constant. So if I take this function right here. Okay, and I do a little add subtract trick here. So I'm gonna have 2x. Okay, let's be careful about how I do this. Okay. 2x minus 4 plus 4. Yeah. Okay. All over 2 minus x. So I write the 4 over 2 minus x. And then what's left is plus 2x minus 4 over 2 minus x. But that's the same as if I factor a minus 2 out of this fraction. Actually, yes. And these cancel. So sure enough, the first function g I have is the same as the other function, except minus 2. So they really do differ by a constant. Yes.
I know I came in just like a little late, but, what does this have, like, I'm kind of lost on where this all began.
Okay.
Like, what would a sample question of this be asking, and what would the answer be?
Either given a function, find its power series, or vice versa, given the power series, find a function. That kind of question, based on what we've seen up to this point, could only be practical for a very limited category of functions. Functions you can easily relate to a geometric series. By being able to carry out derivatives and integrals also, we can find power series for a wider category of functions. Because this function right here, that's the goal. We're trying to find a power series of this.
So so we would be able to recognize this because it would give us both f of x and g of x.
If I feel like giving a hint, yes. But the support we will recognize is, and that's what you're going to see from these examples, and why I'm doing these examples. That something like a function like this, you already know from before how to express that as a sum of a geometric series. Because you can divide top and bottom by 2. But what happens when you take the derivative of this? You get this denominator squared. So there are certain patterns like that happen. So, or if I was taking the integral of this, I'd have a log. So based on things that you see in your function that you're given to work with, that's going to tip you off. Like, oh, I'm going to have to take a derivative of this to relate it to a geometric series or an integral. Okay. Now, in the notes, I've worked with this function right here. But to give you more variety to work with, I'll work with this one. So, and yet I should have written the goal up front. Find power series of this function. Squared. Now, given that this function is a derivative of this function, where h of x is the antiderivative of bound over there. What you can do is find a series for h of x first. All right, and then since h prime is f, we take the derivative of a series for this. So that's the plan.
I was also trying to find your notes online and I found like a link to like a free calculus textbook.
Oh,
That was the only thing I could find
where were you looking?
on your Canvas page.
For,
Am I- am I-
for today's class?
Oh, no, not for today's. Okay, so you posted for each day's class, the notes?
Yeah, so if you go to the main page, you see, Math 169 class meeting for whatever date,
Okay,
the notes are there.
okay.
Now,
I was looking for just, I thought someone said it was like 190 page something.
okay, further up, where it says it's, click here to access for lecture notes. That's the big document.
Okay, you know what? I probably thought those were the videos you've been recording.
Okay, well, the videos are under those, dated items too.
Okay. All right, appreciate it.
All right, any questions before I carry this out? Yes, so when I set up the Canvas item for each class, I put the notes there, and the notes might change as a result of what happens during class. But at least you have something to go on if you'd like to follow along during class. Okay. So the first thing to do, find a series for this function. X is 4 over 2 minus x. And this we know how to do from before because we can relate it to a geometric series. But I want to write it that way where I have 1 minus something in the denominator. So what I can do is I can divide top and bottom by 2, just to make sure I get a 1 there. So this is saying it's 2 over 1 minus x over 2. Now, that is the sum of a geometric series a r to the n, where a equals, so what does a equal in this case? Yes, the numerator, and then what is r?
X over 2.
X over 2. Okay, so now we can fill these in. Sum n equals 0 to infinity of 2 times x over 2, all raised to the n power. Okay, now what I like to do when I write a power series is whatever power of x I have, I'd like to have that written separately, and then everything else is a coefficient. So I have 2 divided by 2 to the n. So that's 1 over 2 to the n minus 1 times x to the n. So that is my series for h. Actually, the function I was going to work with, the other antiderivative, the series is exactly the same, except it starts at n equals 1. Right. Okay. Now, the next step is I differentiate term by term. So the function I want the power series for, which is 4 over 2 minus x squared, that is h prime of x. That would be the derivative of this whole series. And then, derivative of all that. So we take a derivative term by term. So we have 1/2 to the n minus 1, then I have n x to the n minus 1, and I'm going to start from n equals 1 because, as we saw before, the first term is just going to be 0 anyway when you take the derivative, because the first term of a power series is always a constant. Okay. But then what I can do is carry out an index shift, go ahead and start at n equals 0, but because I'm decreasing the starting index by 1, I need to bump n up in my expression inside. So wherever you see n, you replace it by n plus 1. So this right here is the final result.
That is the answer.
That is the answer. Yeah, because the goal is to compute the power series for f using the fact that it's a derivative of this function for which we know how to get the series. This is a geometric series, so when does it converge?
X over 2 is less than 1.
Yeah, but r here, x/2 has to be less than 1 in absolute value. So another way of putting it is absolute value of x is less than 2. So 2 is the radius of convergence of the first series. But because differentiating term by term does not change the radius of convergence, the same is true over here. So r is again 2. What we need to be careful about is that although differentiating and integrating does not change the radius of convergence, that doesn't necessarily mean that the interval convergence is always the same. It depends on the particular series. Now, this is a geometric series, so x/2 has to be strictly less than 1 in absolute value. So at the
So what's happened to the 2 in front of the x/2 to the end?
so I just multiplied both sides by 2 to get to the radius of
No,
convergence.
not x/2. I'm talking about the 2 back at the h. Okay, so left.
Oh,
All right,
this?
there's 2 right there, yeah.
That doesn't play a role in determining when it converges.
Okay.
Because if a series is known to converge or diverge, multiplying by 2 is not going to change that. So for this series, the interval of convergence is x between -2 and 2, because the center is at 0, and you can go plus or -2 in either 2 units in either direction. Now, if I plug in one of the endpoints, x equal to plus or -2, this r is going to be plus or -1, and that's going to diverge. So that's why I need to have strictly less than in this case. Now, for this series, the interval is again x strictly between -2 and 2, because what happens to this series if I plug in x equal to plus or -2? look at what kind of series you're getting. How do you know that it diverges? If you plug in x equal to 2, terms of your series are n plus 1. Terms are going off to infinity. Terms don't even go to 0. If I plug in x equal plus or minus 2. So that's why, so in this case, the interval convergence happens to be the same. Okay. Any questions about how this one played out before I do another? So in the notes from this example, I've worked with the other antiderivative, which was 2x over 2 minus x. And so the process is generally the same. Like I said, the series for that antiderivative, which I label as g of x, is almost the same as this series right here. So in this one, we're going to find a series, our series for this function. Half inverse tangent of x minus 2 over 2. Now, that is definitely not something you can easily express as a sum of a geometric series. Don't even bother. So when you have a function like this, it doesn't look very geometric series-like at all. What we want to do is see if taking its derivative or integral will help. So in the previous example, 4 over 2 minus x quantity squared didn't look very geometric either. So the thing to do in that case was take its antiderivative. I'll bet that I don't even know what to okay, what the antiderivative of arctangent even is.
Plus x.
That's the derivative of arctangent, and that's what we're actually going to use here. In fact, so integral of arctangent, I don't even remember that off the top of my head, which I probably should be embarrassed about, but okay. So okay, you go the wrong way all the time. All right, so let's go ahead and take the derivative of this, since that's something we know how to do. Because the derivative this plain old inverse tangent of x is 1 over 1 plus x squared. So that's what we'll have in this case. We'll have the 1/2 is just sitting there, and then we take 1 over 1 plus whatever you're taking the inverse tangent of, and the whole thing squared. And then what else do you need to do? To complete taking the derivative? That's a derivative of what's inside, which is what?
Wait, oh, no, no.
Go a little further. Yeah, we get another factor of 1/2. Okay, now let's clean up the mess. So I have 1 over 1 plus x minus 2 squared plus 4 times 1/4. Okay. Actually, you know what? I'm gonna leave that the way it is. Okay. Because in the notes I have the function all cleaned up, but that actually works against us or slows us down a bit. Because we're looking for a function that we can express in a geometric series, and that requires having, you know, 1 in the denominator, which we have. So that's good. Okay. Now, well, what I want to do is express this as a geometric series. A r to the n. In this case, I can do that. What is A?
1. Oh, wait, yeah, 1.
Nope, not 1. 1/4. Yeah, so whatever's multiplying the fraction. Actually, right, so that it's a 1 down here. That's the A. What's the R? Yeah. So because we have a plus down here, that tells us R needs a minus, and then whatever is sitting there gives you the rest of R. Okay. So now I have my geometric series. So f prime of x, we're still dealing with a derivative. Going to be 0 to infinity of A. So I can just go ahead and fill in the A, and then the R. Oh, wait, gotta be careful about that. Minus x minus 2/2, the whole thing squared, and then all of that, the entire R, is raised to the n power. Let's label everything here. Okay. So now I want to write this in a form where if a power of x minus the center, which is 2 in this case, a power of x minus 2 written separately from everything else. That'll make things easier when you go to take the, in this case, we're finding a series for the derivative of what function we want. So once we're done with all this, we're going to take the integral of that. So the 1/4, and then here we have minus 1 to the n. And then x minus 2 to the 2n, multiplying these exponents. And then I have in the denominator 2 to the 2n power. But 2 to the 2n, that's the same as 4 to the n. And I have a 4 sitting there already. So I can write this as minus 1 to the n, 4 to the n plus 1. And then I have x minus 2 to the 2n. We only have even powers. Questions so far? Now, we integrate term by term to get the power series of the function we want, which is f. So that's the integral of f prime. So that would be the integral of this series. So all you do is you write the series itself, except once you get to the x minus the center to a raised to a power part, and this part you just replicate as is, you just apply the power rule only to that. That's the only part that depends on x. So Okay, so when I take the antiderivative of just this, what's that gonna give me?
UN plus one over UN plus one.
Yes. Okay, so that part's taken care of, but I'm not done. What else do I have to write here because of what I just did? Plus C. Yes, you still have to concern yourself with the plus C. So we're almost done. Just have to deal with that. So to figure out what the C is, we need to go back to the function we're trying to find a series of in the first place. Our tangent monstrosity.
Yeah.
So what we know is that that function, 1/2 inverse tangent of x minus 2 or 2 equal to the sum 0 to infinity of -1 to the n, 4 to the n plus 1, and then you have -2 to the 2n plus 1 over 2n plus 1 plus c. So we're going to use this equation that I've just written out to figure out what c must be. And the way you do that is you set x equal 2 on both sides. Why 2? Because it's the center. So whatever the center of your power series is, that's what you plug in. And the reason why you do that, when you've just done term by term integration of a power series, when you plug in the center, the entire series will be 0 because you have only strictly positive powers of x minus the center. So then you just left with c on the right hand side. So c will turn out to be your function that you started with, evaluated at the center. So it's this. I'll use a vertical bar to indicate I'm plugging in x equal 2, but that's going to give me 1/2 inverse tangent of 0. But what is inverse tangent of 0?
Is it part of the two? Or is it?
No,
0.
it is 0.
Okay.
Yeah, because tangent of 0 is 0. So, psych, we don't need this after all. In this example, it turned out nothing, but for other examples, you might. So that's why I'm going through this whole stuff because you never know. Any questions about how that one played out? One more. Now, here the goal is a little different. That before you're given a function, the goal is to find a series for it, either by term integration or differentiation. Here we're dealing with a function for which we know how to get the series from what we've learned before, but we're going to use that knowledge to work out an integral. So trying to estimate this integral, 0 to 1 of 1 over 1 plus x to the 4th dx. Now, if I had written 1 over 1 plus x squared, you know how to do that. You say, oh, it's arctangent, and then you get pi over 4. But since it's x to the 4th, if you want to try every single integration technique that you've learned, okay. That would be a real pain. The only thing I could think of off the top of my head is because since you have a polynomial downstairs that you can, normally what you would do is try to factor it, and you'd have either linear factors or irreducible quadratic factors. But yeah, that's yeah, some bites. So we're not going to do that.
Matrix substitution.
Maybe you're gonna try this afterward, aren't you? Or maybe you can try it right now. But we're not gonna do any of that. We're gonna use power series. We're not gonna try to evaluate it exactly. That's a challenge for someone else. So
Let's keep it that way.
yeah, okay. So we look at our integrand and try to represent it as a geometric series that we can certainly do. So what is A, what is R?
A would be just 1.
A is 1,
R is x4, x to the 4th.
almost.
Negative.
No,
Negative.
negative.
It's whatever subtracted from 1, minus x to the 4th, okay. So we get infinity, so we have minus 1 to the n, and then x raised to the 4n. Okay. So now what we can do is substitute this into the integral. So the integral from 0 to 1 of our function all right, well, I'll just fill in the series. But because of the linearity of the integral, the summation sign you can pull out. And anything that doesn't depend on x, you can pull out. So minus 1 to n, minus 1 to the n power also can get pulled out. So I have sum of minus 1 to the n. Then I have the integral from 0 to 1 of x to the 4n. All right, so then you just doing a simpler integration on that. Some might find that boring, but so this is going to be x to the 4n plus 1 all over 4n plus 1. When you plug in its limits, 0 and 1, so you get minus 1 to the n, and then plug in limits 0 and 1, and you just get 1 over 4n plus 1. So if you were able to figure out the sum of this series, that would be the value of the integral. And hopefully the series converges, but it does in this case, because what kind of series is this? It is an alternating series. The absolute value of the term is this 1 over 4n plus 1. That is decreasing. It's going to 0 as n goes to infinity. So this whole series does converge. Don't worry about that. So we may not have a quick way to get the value of the sum, but to get an estimate of the integral, which is the best that we can hope for, We can use the alternating series estimation theorem. I'll refresh your memory as to what that is. We're doing, I'll write straight out, generic alternating series. Minus 1 to the n, bn. And if we know that the series converges because of the alternating series test, if I let S refer to the sum of a full series, and if I let SK be the kth partial sum. So instead of going up to infinity, I stop at K. The alternating series estimation theorem says that the absolute value of difference between the true sum and the partial sum is less than or equal to the next term. The absolute value. So I want to find value of K so that the error, full sum minus the kth partial sum, is less than or equal to, let's say, 10 to the minus 3. And so I want to make sure I have 3 decimal places, regardless of how it's rounded. Okay, so based on this, I want the next term in the series. So that would be, so I'd be taking this fraction here and replacing n with k plus 1. So I'd have 1 over 4 k plus 1, which is the same as 1 over 4k plus 5 is less than 0.001. So I just have to solve that inequality for k, and that'll tell me how many terms I need to make sure that I have that much accuracy. Now, if I rearrange this inequality, that tells me that 4k plus 5 must be greater than or equal to 1,000. So k is going to be roughly 249-ish. That's bad. So I would need a lot of terms to get that much accuracy. And the reason for that is these terms, they do go to 0, but they go to 0 pretty slowly. So if this had been like 1 over 4 plus 1 quantity squared, for instance, then I would need a lot fewer terms than this. And there's some cases where whatever expression you get, you might not be able to easily solve this inequality. It just depends on the problem. But at least but better than nothing, I guess. Maybe not much better. Okay. So this is one application of power series, because power series are good for representing or maybe approximating functions by polynomials. And we like polynomials because they're easy to work with when it comes to derivatives or integrals. So however nasty, if you're trying to evaluate an integral, however nasty the integrand might be, if you're able to come up with a power series for it, then you have the easiest thing in the world to integrate, and you can at least If it's a definite interval, you at least get something that's in the ballpark. Any questions about this one? There's,
Where did you get the 10 divided by 30?
that's fixed value.
Okay.
Um. Yeah, so the goals of some of these problems is trying to answer is accurate to some tolerance. Most precision you can hope for when it's a computer that's doing the work is roughly 10 to the minus 15. That would be a whole lot of terms.
Yeah, that's a little too much.
Yeah.
What's like the max, like, would you tell us that you want to like 10 to the negative third on a test?
Yeah, something that would have to be specified.
Okay.
Actually, check. What do I have on the test in this area? I don't necessarily have anything, but it could be could be in a homework.
Yeah, let's take a look at the test real quick.
Well, I'll take a look at the test. Okay. Oh, okay. I actually don't have a problem like that, like what I just did on the test. So as far as problems related to power series at all, there are only two. So there's one problem
Yeah, but how
where,
many questions on the test? Like five?
well, yeah, 12 total.
Well, some of these are really time consuming. That's what I was saying.
I reserve a right to curve if need be,
Okay.
but I also reserve a right not to curve. If you're all gonna like conspire to do the academic equivalent of point shaving and all do poorly, then I'm not gonna, that's not gonna go well for you. So, unfortunately, I have to keep in mind that what may have been suitable for a test in terms of how many questions you put on it for this class, 10 years ago, might not be as suitable now. I don't really know. I have no data on that. I am making problems less evil than I did. No, I guess I kind of have a confession to make. I didn't really mean to be doing this, but when I looked at problems that I gave last time I taught this, 2012, like a few times before that, it's like, wow, what was I doing? No wonder they hated me. No, I mean, they didn't, but well, there were a couple who did.
Sure, someone did.
Yeah. That like ones we're trying to get a function, a power series for a function or vice versa. That are you can make a problem that's, not too bad or pretty unreasonable, because there are all kinds of things you can do to manipulate a power series. You can replace x by a constant times the power of x. You can differentiate, you can integrate, you can multiply the whole thing by a power of x. So if you have a problem that requires several of those operations all at once, that's a pretty nasty problem to put on a test, so I'm not doing it.
So a lot of the questions will be based, or a majority of the questions will be based off the series prior to power series, like geometric ratio.
Yes, particularly geometric. So one problem I give is you're given a power series and it just asks for the radius and interval of convergence. So that was from a couple classes ago where I did a zillion examples of that. The other one, you're given a function f of x. Find the power series for it. Oh boy. So I'm looking at the real test. And no, the problem I gave would be too easy based because it's too similar to an example I just did today. So
Let's have a little mercy, okay? It's Easter.
this is the first time
It's time of
this
forgiveness.
is the first time I'm giving you the list of convergence tests during the test. There's already been some mercy. So, all right, we'll see. Okay. All right, but what but it'd be something along the lines of what I showed you today. And also the previous class where I also was using geometric series to come up with power series. And that's all. Yeah, around this time I'd be including Taylor series on a test too, but since I'm covering that while I'm away, I didn't feel right doing that. And I might decide not to put them on the final either, it just depends on my mood, so. Okay, all right, well, oh, wow, I'm past time. I didn't expect that. Sorry about that. Okay, get out. Well, I'll keep the Teams meeting running. I'll stay here in case anyone has questions.
Next week.
Actually, one, I won't be here.
Oh, that's right.
Yeah.